So this is part 2 of lecture number 10, Conveyor models. And this is material that is covered in section 10.8 of your textbook. The section title is Fixed Path Material Handling Models. So the material that we are covering in this lecture is part of the first objective for this class, which is develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. And as I mentioned in the first slide, this is part 2 of our lecture, so we already covered the first bullet in blue, the conveyor loop with deterministic loading and unloading sequences. We had a lab on Wednesday in which you practice how to design a conveyor and basically determine the capacity of a car for a conveyor that is unidirectional in a loop. And today I'm going to start from there. I'm going to go over the example one more time, and then I'm going to transition to a conveyor loop with Poisson arrivals. So the conveyor loop with deterministic loading and unloading sequences, this is what we cover on Monday and Wednesday. So here's the type of problem that we are trying to solve. I'm not going to spend too much time on this example, but this is just to give you a reference point. So this is the type of problem that we were solving for deterministic loading. We have a conveyor that is moving cars around the stations. The stations are represented by circles. The conveyor is the line with the dots. The dots are representing the cars. And for this type of problem, we were trying to determine the capacity for each car. So this is the description of the methodology that you follow in order to get to that solution. And this is something that we already discussed in class. So when solving this problem, in which we have 9 carriers equally spaced in 7 periods for loading and unloading, we were able to determine that the capacity for each one of those 9 cars should be equal to 5, which is the value of B. And in the lab that we worked on Wednesday, we showed that by increasing the number of cars for our conveyor, that doesn't really mean that we are going to reduce the capacity for our cars. We noticed that by increasing the number of cars from 9 to 10, actually the capacity required for each one of those cars increased. So that's what I'm trying to illustrate here. Now suppose that distance from station 2 to station 1 on the conveyor is changed, such as the loading and unloading sequences are now given by these two sets. And by solving the sequences, by doing the procedure that we performed for the exercise in the example discussed in class, and also for the lab, we can obtain the values for H1 and H2. So using those values, we can determine that the capacity required by using those new sequences for loading and unloading is now 4. The example illustrates the effect on HIN of the location of the station served by the closed-loop recirculating conveyor. Not only can the capacity requirement for the carrier be affected by the number of carriers on the conveyor, but it also can be affected by the location of the stations around the conveyor. Okay, so now we can talk about the conveyor loop with Poisson arrivals, which is the next topic for this lecture. So we are also concerned with the performance of a closed loop unidirectional recirculating conveyor with stations located around it. However, this time each station is either a loading station or an unloading station, so no station performs both types of operations. There is an input-output queue for each loading unloading station, and as opposed to the following deterministic pattern, items are loading station I are placed one at a time in the input queue of station I according to an independent Poisson process with rate lambda I. So I'm pretty sure that all of you have taken the course in engineering statistics. So in that class we discussed what a Poisson process is. So meaning that we're going to have a certain number of variables that are independent happening within a specified time period. The conveyor consists of equally sized windows. Each window holds at most one item. Various conveyors, such as the trolley conveyors, in which the carrier is going to be equal to the window, the tilt tray conveyor, in which the tray can be equal to the window, and the cross belt conveyors, in which the belt position is equal to the window, fit the second model, which is the one for Poisson arrivals. The conveyor has a user-specified constant length and speed, and the length is expressed in number of windows, and the speed is measured in the number of windows passing by a fixed point per unit time. So here are the description of the parameters that we are going to be using for this type of problem. First, we have capital Pij, which is the probability that an item arriving at a loading station I needs to be delivered to unloading station J. Fij is the flow rate from station I to J, and to find that flow rate we need to multiply the lambda values, which is the rate of arrivals for I. So going back here, in which we define I, times that probability. Suppose that are M loading and N loading unloading stations, then we have theta equal the set of loading stations, omega denotes the set of unloading stations, and lambda denote the rate at which the conveyor delivers loads to the output queue at an unloading station J. So for the conservation of flow, we must have the following relationship satisfied, which is the sum of all lambda I should be equal to the sum of the capital lambda values. So remember, this must be satisfied at the end of your solution. Okay, so to derive the stability condition, the conveyor loop is divided into k segments denoted by S1, S2 up to Sk, where k is equal to m plus n. We go back here, m are the number of loading stations and n is the number of unloading stations. Okay, so as shown in the figure, Si represents the set of windows on the conveyor between station I minus 1 and station 1. So here we have our first station and our second station, and we're going to have a conveyor moving items from here up to here. By definition, each segment Si ends with a loading or unloading station I. Delta I denote the required flow, this is delta, rate, or the items per time unit in conveyor segment Si. And delta I is equal to the sum of K and L of the values of F times Z. And we had the definition for these parameters. F was defined earlier, is the flow rate from loading station K to unloading station L, and ZKLI if it is equal to 1 if the load from station K to L travels through the segment Si, and 0 otherwise. Okay, so this is a value that is going to be assigned depending on the situation of the conveyor. Then we have capital V, which denotes the speed of the conveyor, and QI denote the ratio of the required flow rate in segment I to the speed of the conveyor. QI is computed using delta I divided by the speed of the conveyor. Okay, so based on the research performed for this type of problem, we can establish the following relationship in which we have, for this ratio, lambda I divided by the velocity minus the delta I value. If that ratio is less than 1, this is a necessary and sufficient condition for loading station I to be stable. That is, in steady state, each item arriving at the input queue of station I will be eventually placed on the conveyor if the above inequality is satisfied. The above inequality can be rewritten in the following way. This is defined as the stability factor for loading I or SFI. So the stability factor. Hence, the conveyor loop is stable if and only if the stability factor is less than 1 for all values of I. That is, if and only if this ratio is less than 1 for all the stations. So I, if you remember, theta is defined as the set of all stations. Okay, so what we are trying to do here is we want to determine if we can reach this stable condition for our design. So here we have an example. We want to determining the minimum required conveyor speed. Consider a closed loop, unidirectional conveyor loop with 52 windows as shown in the figure. So figure 10.55, this example is coming from your textbook. So that figure is this conveyor right here. 4 stations are located around the conveyor. Stations 2 and 4 are loading stations. So 2 and 4 are loading, so that's why we have these arrow pointing in that direction. While stations 1 and 3 are unloading stations. So we have 1 and 3, and for those items are going out. Suppose that the rate or the lambda rate for station 2 equals 30 items per minute, and the lambda rate for station 4 equals 20 items per minute. Furthermore, suppose that the probability for 2-1 equals 0.6 and the probability for 2-3 equals 0.4. Probability for P of 4-1 equals 0.25 and the probability for 4-3 equals 0.75. Assuming the conveyor turns in a clockwise direction, determine the minimum speed required in windows per minute to ensure that the conveyor loop is stable. So that's what we're going to do in this example. So the first thing we're gonna compute is the flow rate from station I to J. So we have the flow rates for F21, F23, F241, and 43, which are our loading stations. We have the values of lambda for each one of the stations, and we also have the values for the probabilities. So that's how you compute those flow rates. With clockwise rotation, the 4 segments on the conveyor are defined as follows. So we can define segments as follows. So we start with 1 up to 11. That will be this piece right here. Then we'll go from 12 to 28, which is all this up to here. And then we go from 29 to 35. And then the last segment is the one that goes from 36 to 52. The 2 segments that end with the loading stations are segment 2 and 4. So that's this segment and this segment. So this is 1 and 3. So segment 4 and 2 are the ones that end with the loading station. Given the above Fij values for segment 2 and 4, we can compute the delta I values. The required flow rate, items per unit time in the conveyor segment Si, is computer next. So we first need to compute the delta I values, which are 15 and 18 for segment 2 and 4. And we know that the conveyor loop is stable if and only if this condition or ratio is satisfied for all the stations. That is, we need the velocity to be greater than the lambda I values plus the delta I values for I equals 2 and 4. So we know the lambda values and we know the delta values for each one of the stations, so we can compute the velocity. So for station 2, that value is going to be 45, and for station 4, that value is going to be 38. So the conveyor speed must be greater than 45 windows per minute if we want our conveyor loop to be stable. And that concludes this topic on Poisson, conveyor loop with Poisson arrivals. The homework that is assigned is now in tracks, so you can look at the homework. You're going to have problems coming from this topic and the topic that we cover in our previous lectures. Thank you.